Yeah, sure, thanks. Yeah, so the first talk will be given by Dr. Longbo Huang. Dr. Longbo Huang is an associate professor with tenure at the Institute of Interdisciplinary Information Sciences at Tsinghua University. And Dr. Huang's research focuses on AI for decisions. He serves for many PC members and organizing committees for many conferences. And Dr. Huang serves as on the editorial board for ASM, PAX, and TON. And Dr. Huang received the Outstanding Teaching Award from Tsinghua University in 2014, the Google Research Award and the Microsoft Research Asia Collaborative Research Award, and also in the same year, and was selected into the MSRA Star Trek program in 2015. Dr. Huang also won the ACM Symmetry Rising Star Research Award in 2018. So Dr. Huang, if you have prepared well, you can just start.
Right. Thank you very much, Professor Lee, for the kind introduction. Can you see the slides as well as myself?
Yes.
Okay. So thanks a lot. Also, thanks a lot to Professor Wei Chen for the kind invitation. I'm Longbo Huang from Tsinghua University. It's my great pleasure to join this workshop and to share with you our recent work on HeavyTailed multi-arm bandit. So this is a joint work with my student Jia Huang at Tsinghua University, and also a junior student in the Yao class, Yan Dai. Okay, let me start by talking a little bit about the multi-arm bandit model, because I know that many people work on this. But anyway,
sorry, Dr. Huang. Yeah, saying the mode. Yeah, we can see the full slides, or can you just switch the mode?
Sorry, can you see or can you not see?
Yeah, I can see the slides, but can you turn it? But I can also see your notes. Yeah.
Oh, let's see. Let me see if I share the desktop. It's easier. How about this?
Oh yeah, this will be better. Yeah.
Okay. Because I cannot see what I don't know what you're seeing. So, all right. So the multi-arm bandit model. It's actually a very classical model in online learning and has found many applications in the important areas. And so I'll give you a few examples. So the first one is online advertising. So in this case, basically we need to figure out which advertisements are worked better for which users. And so somehow we need to learn the effectiveness. But at the same time, we also don't want to spend all the time learning, because then the companies will lose revenue. In wireless communication, so each of the channels have different qualities. So the base station may have to probe different channels to learn about their quality to decide what channels they're going to use, so that they can maximize the amount of data volume, the data that's being transmitted. In clinical trial, you want to figure out which drugs are more effective for which disease, and so, but at the same time, you also don't want to basically be doing experiments. You want these trials to also be effective, and you can cure patients better. In recommendation system, you want to recommend items to users, and so you want to learn which items are more favored by which users. But then similarly, you don't want to spend all the time learning, because then the users will not be very happy. In many of the sort of machine learning training and also the AI models, you want to figure out which sort of model or experts are more effective, but you don't want to spend all the time learning. You want to learn the model's effectiveness and at the same time maximize the performance. Also in finance, you want to figure out which investment option or combination is more effective. And at the same time, during your investment process, you also want to maximize your revenue. So we can sort of see from these applications or these examples, there are many more examples. We can see from these examples that the MAB model really captures this fundamental trade-off between exploration and exploitation. That is, you're given a set of unknown options. You want to figure out how good they are, but at the same time, you don't want you want this process to be fruitful as well. Okay, and because of its generality, I think the multi-arm bandit model and many of its invariants have been extensively studied in the literature by many talented researchers, including many of the speakers and the organizers here. And I think this work is by Professor Yuan Zhou. This is by Kuroki. This is by Yihandu and Professor Chen, and by Siwei and Professor Chen, and also by Professor Shirley herself, and many others. I'm just giving a few references here. And so let's take a look at the concrete multi-Bandit formulation. So the problem setup is as follows. So I'm talking about basically the most basic version of it. So the idea is that we are going to play the game for capital T time steps, and we are given a set of K actions, which are called arms, and we're also given these T times K loss matrix. Basically specifies at which time if I pull a particular arm, the loss I'm going to suffer and observe. And then the game is as follows. So at each time we're going to choose one particular arm, denoted by A of T. And after we put arm, we're going to observe and suffer this particular loss, denoted by L of T comma A of T. And then our objective is to minimize the following definition of regret, which is the expected difference between the cumulative loss that we suffer minus the cumulative loss that would have occurred if we stick to a single arm. Okay, and we want to maximize that. Okay, and then depending on how this loss value or this loss is generated, for example, whether or not it's from an IID process or it's chosen in a bounded region, we get either the stochastic version of the MADB problem or the adversarial version of the MADB problem. Okay, so I hope that I explained this basic setup clearly, because this is and you can sort of see this formulation is fairly general, despite the fact that it's a very concise and beautiful model. Okay, all right. So in our work, we actually generalize this formulation, and we consider the following HeavyTailed version of the multi-Bandit problem. That is, we still play the game for capital T times. We are still given a set of K arms. We similarly have the loss matrix, except that now each of the loss is decided as follows. So there's an adversary who is going to pick this alpha sigma HeavyTailed distribution. So he's going to pick a set of distributions, so denoted by nu of T of I. And then each of the reward or loss is going to be generated from these distributions. Okay, that is, if we put an arm A of T, then its loss is generated from this particular distribution nu of T of A of T. And we only constrain this distribution to be such that its alpha's moment is upper bounded. And here alpha is something that can be that's greater than 1 and less than or equal to 2. So in a sense, if alpha is not really 2, it's something smaller, then you may end up having a case where your second moment is not bounded. Okay. All right, and then similarly, we want to minimize the regret, which is defined as follows, as before. Okay. Okay, so the key generalization here is really we consider a case when the loss is generated in a HeavyTailed manner. Okay. All right, so this is a natural generalization in both directions. First of all, so if we stick to the case where all these distributions are the same, then we have the stochastic HeavyTailed multi-Bandit problem. And on the other hand, if we constrain these distributions to be Dirac measures at the boundary region, then we get the classical adversarial multi-Bandit setting. Okay, so this is the setting that we are focusing on. Okay, let's take a look at some of the challenges. First of all, as I said, depending on the value of alpha, we could have potentially unbounding second moment, and we all know that for those of us who are familiar with the multi-Bandit literature, we know that this is going to cause some problem to the estimation of the loss, and also as well as deriving some of the nice concentration results for bounding the regret. And the second is these alpha and sigma values. When they're unknown, it's also very challenging, because somehow we need to figure out a way to adapt to those values or learn those values. Okay, so these are the issues we're facing. Okay, all right. Some of the representative prior results on HeavyTailed multi-Bandit. So in particular, so Bubeck et al. In 2013, they established a lower bound for the stochastic HeavyTailed multi-Bandit problem. They also proposed this robust UCB algorithm, again for the stochastic case. And then there is Li et al. Deriving a bound which is not suboptimal for the stochastic case. And Zimmer and Seldin in the 2019, they did propose this half SALIS-INF algorithm for both the stochastically constrained adversarial case as well as the adversarial case, and derive these bounds. But in this case, they focus on the case where the losses are bounded. Okay, and our results are the following three. I'll go over them in details later. But from this, one thing to point out is that most of the prior results, they require knowing sigma and alpha beforehand when they design their algorithms. Okay, so we see how we can sort of relax this assumption, and also we want to see if we can design algorithms that can achieve good performance in both cases at the same time. All right, so our contributions in this work are that we propose three novel algorithms. The first one is called the HeavyTailed SALIS-INF, or HTINF, is H-SALIS-INF. This algorithm actually requires knowing sigma and alpha, and it's the first algorithm to achieve the best of both worlds regret for the HeavyTailed multi-bandit problem. And by that I mean that we can use a single algorithm and we apply that to an environment, whether or not it's stochastic or it's adversarial, is we don't really need to know that. Even if we don't know that, we can still achieve the best possible regret for both environments. And we also show that we can apply the HTINF algorithm to the case where we actually do not know sigma and alpha. And in this case, we call the algorithm up-TINF. And we show that it can achieve a log-T regret for the stochastic case, and also a small OT regret for the adversarial case. And then the last algorithm we propose is an adaptive SALIS-INF algorithm. It actually requires zero knowledge of sigma and alpha, and we show that it achieves a minimax optimal regret for the adversarial setting. Okay. So I'm going to go over the algorithms and talk about the analysis sketch. Okay, because I don't have time to go over the analysis. So let's see. So we first take a look at the HeavyTailed SALIS-INF algorithm. The high-level idea is that the algorithm builds on the follow the regularized leader framework, and we introduce a novel skipping idea to clip large samples. So remember that now, because the reward can be, or the loss can be HeavyTailed, so we may end up having a case where we face a very large loss value, and if that happens, it's going to cause a lot of trouble to our FTRL framework. And so the high-level idea is that we're going to get rid of this by skipping these large samples. But this is going to cause some technical problem for bounding the regret, and so I'll explain that in a bit. First, take a look at how the algorithm works. So the HeavyTailed SALIS-INF works as follows. So this is the timeline. So at time t, what we'll do is that assuming that we already have this probability distribution for choosing the arms from the previous step, what we'll do is that we're going to put an arm A with the probability of x of t of A at time t. Okay. Now, after we do that, we're going to receive a loss value generated from a HeavyTailed distribution, and we're going to form an estimation of the loss value with importance sampling and skipping. So the expression is this. So for those of you who are familiar with the FTR sort of framework, you see, or EXP algorithm, you see that the last expression here, L divided by X, is something that's commonly used. In our case, we introduce this skipping idea. That is, we specify a threshold R of t, and any loss value that's greater than that, we're going to skip it. So that's shown in this figure here. So we're going to skip anything that's larger than the threshold. And as I said, because if you don't do that, we essentially allowed very large loss samples to enter the FTRL framework. And because of the potentially unbounding second moment, we may have, we actually run into technical difficulties for analyzing that. So by doing the skipping, this is going to help us to analyze the regret using, again, under the FTRL structure, but it's also going to give us some other nice features, but except that now this is no longer an unbiased estimation of the loss, and we have to handle that. And after this step, so we see that we already put down, we already have the observed the loss, and we also form the estimate. what we'll do is that we're going to perform an FTRL step to generate the action, the distribution over the actions in the next time step. Okay, and here just want to emphasize that we're actually using the 1/alpha Sellis entropy as a regularizer. Okay. Okay, so I hope that explained the general flow clearly. So the idea is that essentially we're running an FTRL, except that we, on top of that, we introduce a novel skipping idea to clip the large samples to make sure that the FTRL structure works well. And then we will basically handle these issues that's due to this skipping idea. So here I have the pseudocode for the HTINF. The details are not important. I just want to highlight a few of the places. First of all, here we use the 1/alpha Sellis entropy. And then this is the follow the regularized leader action. And then this is our skipping threshold. I'll talk a little bit about why we choose it to be like this. And again, the idea is to avoid overly large loss in estimation. And then we also have the importance sampling. As I said, this is now sort of biased because we skip some of the large samples. Okay. All right. Then let's take a look at the performance. So what we show is that the HeavyTailed AdaTINF algorithm achieves the following in the adversarial environment. So I want to mention that so we actually do not know which environment it is. So by this we mean that if the environment turns out to be adversarial, we can show that the regret is bounded by this order. It's k to the 1 minus 1/alpha, t to the 1 minus 1/alpha, and log k. Okay, and then if the environment turns out to be stochastic, then essentially we get this regret, which is OT. Sorry, block T. Okay. And one remark here is that this result is actually a best of both worlds result in the sense that in both environments, the regrets are optimal. And it's nice that we actually do not need to know which environment it is. Okay, so that's kind of nice. Of course, here as I said, the HeavyTailed AdaTINF algorithm actually requires knowledge of sigma and alpha. And the next thing we do is that we actually show that the algorithm can be applied to the case when we do not have sigma and alpha. So the way we do it is that when sigma and alpha are known, we can run HeavyTailed AdaTINF with sigma equals to 1 and alpha equals to 2, and we call this the op-TINF. And we can guarantee that if we do it this way, if the environment is adversarial, our regret is this. So not read the whole thing, but it's essentially a small t. If the environment turns out to be stochastic, then we achieve log t regret. Of course, the constants multiplying are slightly worse compared to the previous case when we do know these values. Okay. Now, as I said, we can still achieve log t regret for stochastic case, but then if it's adversarial, we get a small t. Okay. It's understandable. In this case, we actually do not have information about sigma and alpha, and so it's sort of optimistic version of trying to get the good performance. Okay. Now I'll briefly talk about the analysis idea because this is going to be useful and for explaining our adaptive algorithm as well. So let's see. So first, let's take a look at the regret decomposition of HeavyTailed AdaTINF. So this is a common expression. That is, y here is one hot vector. Mu is the mean of the distributions, and x is our probability distribution for choosing arms. So this is by definition. And then we're going to decompose that by introducing this mu prime, which is this. So mu prime is really, the high level idea is that this is the expectation under clipping. Okay, so it's the clipped expectation. Okay, and this is just by adding and subtracting. There's nothing fancy. And we call the first term skipping gap. And this is really because in our sort of loss estimation step, we skip some of the potentially large loss samples. Okay, and then we call the second term the FTR error. Okay, as I said, because of the skipping idea, we somehow managed to control the range of this loss that's entering the FTRL, the framework. So that enables us to analyze its performance nicely. Now, one thing to notice here is that the skipping threshold actually impacts regret. And the idea is that a larger threshold is going to lead to a smaller skipping gap, as we can see, right? Because then these two values will be very close to each other. But then it's going to lead to a larger FTR error because we allow larger samples to enter the FTR framework. And it turns out that optimal trade-offs is achieved at the particular sort of threshold that we chose. Okay. Of course, I'm not getting into details, but I'm just giving you the idea of how we end up how we carry out the analysis. And analysis idea is that we derive some self-bounding properties for the regret terms, which are similar to the Zimmer and Sarding did in their 2019 paper. And actually, it's the first result for us. It's the first result of this kind for the 1 over alpha salicin regularized FTRL. And prior results done by Zimmer and Sarding, they worked. They did that for alpha equals 2. Okay. All right. I'll quickly go over the steps without having too much details. So in the adversarial case, what we did was that so from this regret decomposition, we actually further decomposed the FTR error into 2 parts. Right. And so for those of you who are familiar with the FTR framework, you'll see that this is something that's usually done. So we divide it into 2 parts. Okay. And then we can bound the skipping gap using the choice of RT. Basically combine that with the properties from the distribution. We can bound that. And then for part A, we use properties from the Salis entropy function, and then we can derive this gap, this bound here. And then the last one, we use property from the Bregman divergence, and we obtained the third bound for each one of them. We derive bounds for each one of them, and then combining them and with some further duration, we obtain this adversarial case. And then for this stochastic case, the analysis is similar here, except that so. In the previous case, we worked with the worst case, and so in the stochastic case, we were able to work with the distribution vector. So similarly, by choice of RT, we obtain this, and by the properties of the Salis entropy, we obtain the second term, and again by analyzing the Bregman divergence, we get the last one. Okay. All right. So that's the high-level idea of the heavy-tailed salicin regret analysis. Next, I'm gonna use the last couple of minutes to tell you the adaptive algorithm, and it's essentially based on this regret analysis. Let me show you what it is. So I want to emphasize here that now we consider the case where sigma and alpha are unknown. Okay. All right, because we do not have this information anymore. So what we do is the following. Now we still consider the regret decomposition, right? As I said, it's a skipping gap plus the FTR error, and we know that this error is part A plus part B, right? So, and then we realize or we observe that these 2 parts, the skipping gap and the part B, they're actually both decreasing in the skipping threshold, whereas part A here is increasing in the skipping threshold. Okay, and so this gives us the idea that we're actually going to adjust the trade-off between these 2 parts during the execution of the algorithm, and the hope is that by properly balancing them, we can get good regret performance, even in the case when we do not know sigma and alpha. And how to do the adjustment? Well, we actually used the doubling trick to tune both the learning rate and the skipping threshold. And the high-level procedure is as follows. Similarly, we pull arms based on our probability distribution, and then we're going to receive the loss. We form the estimation using importance sampling and skipping as well, except that now we do one more thing. That is, if we realize that the cumulative part A regret or the part A terms is smaller compared to part B and the skipping gap, we're going to double the threshold. And after we do that, well, we perform the FTRL update to generate the next action distribution. And here we use the 1/2 Salis entropy. Okay, and that's the high-level idea of adaptive algorithm. And here we have the performance result. So the adaptive salicin achieves the following for the adversarial environment, which turns out to be minimax optimum. It matches the lower bound by Bubeck et al. In 2013. And I want to highlight, I want to emphasize that prior concentration methods typically rely on knowing alpha, and here we can get rid of that. And how to achieve the instance-dependent optimality and best of both worlds in this unknown case, somehow it's still open. We try different ways, but we're still working on it. All right, so to conclude, in this talk, we consider the heavy-tailed multi-bandit problem, and we propose 3 algorithms. The first one is HeavyTailed AdaTINF, which assumes knowledge of sigma and alpha, and it achieves the best of both worlds for heavy-tailed multi-bandit. We can also apply it to the case when the values are unknown, and we still achieve log-T regret for stochastic and a small T regret for adversarial. And we also propose the adaptive AdaTINF, which requires 0 knowledge of sigma and alpha, and it achieves a minimax optimum regret for the adversarial case. And this is reference. This work appeared in this year's SML conference. And so with that, I'm going to conclude, and thank you very much for listening.
Yeah, thank you very much. Thank you very much for the solid talk. So any question from the audience? Okay, yeah, I have a question. Yeah, you mentioned about that yeah, can you hear me? Yeah.
Yes.
Okay, there is one raised hand. The Zhang Shizhuo. Yeah, you can just turn on your camera and your mic to ask your question.
I get back.
Thank you, Professor Longbo. I'm very interested in your talking, and I wanted to learn more about your experiment about the MAB, these models. Can you explanation about the experiment on the training or evaluation to compare with other methods?
Oh, okay, right. So that's an application. I think different people do it differently. So the idea is that by this I mean that there have been people trying to figure out what let's say that you have a set of expert models you want to use for different tasks, but then you don't really know which one works best for which application. So I mean the high level idea is that, well, I can try to sort of explore the effectiveness of the experts. I mean, and then so what you do is that, well, you try to apply experts to different tasks and see how it works. And from time to time, you get samples, and then you try to decide. I mean, during the task solving process, you want to optimally decide what experts you want to use, so that on the one hand you learn which expert is effective. On the other hand, this process is still working sort of nicely in the sense that you solve the tasks so to a satisfactory level. I don't know if that answers the question.
Oh, yeah, thank you.
Thanks.
Yeah, I have one more question about your optimality of your result. You mentioned that you have matched the given lower bound from the previous Bubeck work. Yeah, so you have matched the T order, and how about the other terms?
I think both K and T are good.
Yeah, okay. The order on the T is good, and how about others? The K or sigma or?
Right, as I said, let's see. We can come back here. The lower bound is this. So can you see the my screen? I have to somehow. Yeah. Right, so you can see that the lower bound is here. It's sigma K 1 over, sorry, 1 minus 1 over alpha T to the 1 over alpha. And what we achieve is this.
Yeah, it's almost matched.
Yeah, so it's good.
Okay. Yeah, but for the stochastic case, there is still open problem.
Yeah, we're not able to solve that because, so, I mean, it's still so technical details. So the idea is that we to get this result, we actually have to give up some part of the regret analysis in the skipping part, and so because of that, we're not able to do it for the stochastic case. That's something that we have been struggling with.
Yeah, it seems that the stochastic case is is more challenging in the problem.
Yeah. In the case when we know sigma and alpha, it's good, but when it's unknown, we try different ways, but
yeah, it's indeed a very challenging problem. Yeah, you have make a big achievement. Yeah, a big step on that already. Yeah.
Thanks a lot.
Yeah. So if there is any other question from the audience. Okay, if no, then let's just thank the speaker, Dr. Huang, again. Yeah, thanks for your nice talk. Yeah.
Thanks a lot, personally.
Yeah. Okay.